Welcome everyone. In this video lecture, we will think about a basic concept that MOSFET acts as a current source. Okay. So before that, first of all, we will know what do you mean by current source. So basically, current source we can say current should be constant or independent to the voltage source. If we are considering this first figure, this one is a variable voltage source. So this current Is. So even if we change the voltage Vs, the current will be same Is equals to I1. The current will be constant. So current should be, we can say current should be constant and independent of the voltage source. Okay. So we can say the current in the circuit will be constant, will be constant and independent of the voltage source. Even if we change the voltage source, the current will be same. That is called our current source. Okay, is it okay? So this current will be I1 equals to Is. Okay, this current Is is same as that of I1 even if there is a change in this voltage Vs. Okay, so here we can see this Is equals to I1. If there is a change in voltage Vs, the current will be constant. Is equals to I1. So current in the circuit will be constant and independent of the voltage source. So in very first we told the MOSFET acts as a current source. So a simple MOSFET in saturation region, basically MOSFET in saturation region works as a constant current source ideally. I have written ideally means we have to channel length, neglect channel length modulation. Okay, if we neglect channel length modulation, okay, after neglecting channel length modulation we can say ideally means this lambda, sometimes we can say 0. MOSFET in saturation region produces a constant current source ideally with lambda equals to 0. We have to neglect channel length modulation. Okay, so first of all we have to start with a NMOS. Okay, NMOS, N MOSFET, we can write it N MOSFET. Okay, okay. So first of all, I have to make a simple diagram. Okay, so means I told you the MOSFET is in the saturation region, works as a constant current source. So first this should be some voltage source. Okay, okay. Suppose this one is our NMOS having this terminal is our gate, drain, and source arrow signals. So source and this voltage is our VDS. Okay, and this one is our get to source voltage. Okay, so this device acts when it is operated in the saturation region. Okay, when this one is operated in the saturation region, it's work as a what constant current source. So as we know, the IDVDS characteristics that I am going to draw, we can say this one is our ID. Okay, say this current is our drain current, so ID I am writing, and this one is our VDS. Okay, so if we plot the curve, okay, ID versus VDS, as we know the curve is somehow, okay. we can say this one is the curve. Yes or no? Means okay, or you can extend some more. Okay, when we are considering lambda value, lambda is greater than 0, when we are considering lambda channel length modulation, but without channel length modulation, or after neglecting channel length modulation, we can make it ideal case lambda equals to 0. Ideal case, we can say this one is ideal, and this one is considering channel length modulation, by considering channel length modulation. Okay, so that's why lambda greater than 0. So ideally first we are think about the ideal operation, and we can say that this side is our saturation region, and this side is our all is our linear region, and this should be our VGS minus VT point. Okay, I'm not going to discuss the whole, but this diagram is very famous. Okay, and we have to know the characteristics ID VDS curve. So we can say that this one is our lambda greater than 0. So we can say this one not acts as a better current source for lambda greater than 0. We will discuss it in detail. Okay, and for lambda 0, ideally, even if there is a change in VDS, it will give the constant current. Okay, so but what we observed that there is some limitation. Okay, so there is some limitation, or we can say the some flip side. Okay, flip side, we can say some flip side. There are two flip side, we can say. Okay, two flip side or some limitation with output current not flat. Okay, what we observe, because practical, this one is the practical situation. Practically, practical. Okay, practically it will be like that. Okay, so output current, what we can write, first one, the output current, that is our ID, is not flat for lambda greater than 0. Okay, because practical case, due to, or we can say due to channel length modulation. Okay, this one is the fact. Means if we considering the channel length modulation, the output current is not flat due to channel length modulation. Okay, then this one not excited, then it does not work as a constant current source. Okay, this one is the limitation. Okay, and one more thing, if this one is our circuit, and if we going to make the, what we can say, the a small signal analysis, if we do the small signal analysis. Okay, I am just want to show, so how we will improve the means constant current source concept. So that I am going to first, this one is a gate terminal as we know. Okay, drain, and this one is source is grounded. Okay, I'm selecting some different color. So this one is gate in, drain in, source in, and this one is current source. So this should be our GM VGS, and this should be plus of minus VGS. This should be our GM VGS will be 0, and one more, some output resistance will be there. So make it some output resistance, make it some output resistance R naught. Okay, this one drain in, so some current is flowing. Okay, and this one is our output resistance, so Z naught. So Z naught or R out, we can say, is our R naught. Yes or no? So if we want to go for a better current source, we have to increase this output resistance, because if we, this current is our what ID. So if you want to make a better current source, this resistance R naught will be more. So a small signal model of a constant current source tells us that it has finite output resistance. So the first thing that I want to write in this means the small NMOS small signal model or NMOSFET, a small signal model must have finite output resistance. Output resistance. Okay, that is our R naught here in this case, or Z naught output resistance. So to improve this the current source, we have to increase the output resistance. So I'm so to design a better current source, we have to increase the output resistance of the circuit, resistance or output resistance of the particular circuit. Is it okay? Means to make the this line is important for any current source to generate better current source. Okay, we have to we have to increase the output resistance of a particular circuit. This is very important. We have to increase the output resistance, okay, for a better current source. Okay, so the conclusion, as a conclusion we can write, okay, as a conclusion we can say what is the conclusion. For better means if we increased output resistance, that is our increased output resistance R naught causes better current source. Same thing, better current source. Okay. So this is the concept. Means for any current source, if you are making with the MOSFET, the output resistance must be very high. Output resistance of the, so there are some technique to increase the output resistance. So two famous one for better current source, we can go for two techniques. So one of the famous technique is our, you have know about the cascade current mirror, cascade connection. Okay, so one more is there, degeneration one and cascade one. So first one is degeneration, okay, and the another one is our, so degeneration and another is cascade structure. So, so the cascade structure will give more better result. And degeneration is also one of the approach. So to increase the output resistance. So I will directly making the circuit and I will try to write the. I'm not going to solve. I have already solved in some paper, some other video. Means okay. So means you can solve this one. Okay. In degeneration, what we have to do? Okay, say this one is our RS and everything will be same. Okay, this one is our VDS. Okay, so RS in case, in the very first case, what we can say, in the first case in this one. Okay, I need some more space. So make a line. Okay. Means what I want to show you means in the first case, if we plot ID VDS, okay, VDS for RS0, for RS0, it is somehow like this RS0. Okay, clear? Is this okay? But if we go with some RS, okay, your curve will be like this. Why? With RS greater than 0, because the RS is there, okay, and if we find the output impedance by considering the small signal analysis, and if you go for the Z naught value that I am going to write directly, the Z naught value, the or we can say the R naught value, if we solve, it will come the R naught value of this one, R naught plus 1 plus gm R naught into some resistance R naught. So initially it is R naught, now it is increased. So that's why this one for RS. Okay. So it will give a better current source. Is it okay? Clear this one? In case of cascade connection. So in case of cascade connection, what I am going to make first the cascade structure I have to make. So in this one there are two MOSFET, okay, say some bias voltage say V1, V2 is there, and we have to say this one say M1 transistor, M2 transistor. I am writing this as a R not 1, R not 1 output resistance, R not 2 output resistance. So overall R output we have to find the R output. Okay, so this can be easily find. uh, I am just going for the approximation that it acts as a some resistance R2, okay, R not 2, okay. So the same circuit if we make, okay, means by considering this one, I am saying this is some resistance part, output resistance is R not 2, and this one is the circuit, okay, some voltage say V1, and this one is our drain part, gate part, source part, and this one is our R naught, overall R naught, and it has some R naught value. Okay, better to say this one is our Z naught, or R naught is the output resistance, and R naught one is the resistance, output resistance for this particular transistor M1. So if we find the R output or R naught, we can say the output impedance, or Z naught, anything we can say, it will come. This one R naught 2 acts as a resistance. Okay. So first of all, we have to write the R naught 1 just like this R naught. So but here what we have to write R naught 1, R naught 1 plus 1 plus GM1 R naught 1. Okay, very similar to this one, 1 plus GM, here only R naught 1 into RS. RS is R naught 2. So this should be our R naught 2. So here this one, and if we consider this GM R naught 1 is we can say more greater than R1, okay, means what we can say this one is GM1 R naught 1 R naught 2 square, or we can say GM1 R naught 1 is much greater than 1. So the overall R output we can say simply GM1 R naught 1 R naught 2. Okay, so in this case the output resistance is much higher, so this one will be a better current source. So okay, so output impedance of the circuit is approximately the intrinsic current gain of the first one into second one, multiply GM R naught 1 into GM are not 2. Okay, so this one is the thing. Okay, so now this is all about the NMOS. So for PMOS, that I have to, for PMOS current mirror, okay, for PMOS, the circuit. So similarly for PMOS, what we have to do, there is a PMOS, so make it like this, and this one is connected to the supply. So one voltage source, try to make, okay, and this one will be current will be like this, okay, from VDD. This one is our VDD. So again, this is also the ID. So in case of PMOS, like this one is the structure. So you can also think about the PMOS current mirror. If you know the this one NMOS, so it is easily understand. So cascade structure is more better, give more better result than degeneration. So this is all about the basic. Okay. So this is all about the concept behind the NMOS current mirror, PMOS current mirror, or oh, sorry, NMOS current source and PMOS current source. Okay, so thank you for watching this video. Thank you.